In 6.6, we're going to see how enthalpy relates to the heat that we've been using so far in 6.4 specifically. We kind of talked about this in 6.4 already, but remember that heat and the delta H have the same magnitude but may have different signs. So when we say that it's positive or negative on the delta H, that helps us to designate whether it's endothermic or exothermic. So one phrase that you could use for the symbol delta H would be the enthalpy of a reaction. Ooh, that's fancy. Another property of a system, enthalpy, is defined by the enthalpy is equal to the internal energy plus the pressure times the volume. Now, just to note, I read this somewhere that internal energy, which we did talk about that in 6.1, will not be discussed on the AP exam because a lot of times people will accidentally interchangeably use internal energy and enthalpy. But this is how the enthalpy is defined. And it is a state function, which means that it relies on the states of matter, just like internal energy, pressure, and volume. So the value of the enthalpy could change if it is a gas or a liquid or a solid. At constant pressure, the change in enthalpy of the system is equal to the energy flow as heat. This means that for reactions studied at constant pressure, the flow of heat is a measure of the change in the enthalpy for the system. So the delta H can also stand for heat of reaction, which I think I've said it like that before. So if it's change of, or the delta means change in, then we would take the enthalpy of the products minus the enthalpy of the reactants. We will actually do those calculations later on, I think in 6.8 for this unit, but for now, just know that one way that you could study that is subtracting the values of the products in the reactants. And when the products have a greater enthalpy, delta H will be positive, and then if the reactants are greater, then it will be negative. And that has another way, we've seen that on energy profiles, how we can tell if it's endothermic or exothermic. So what we will do is we will see how this relates given some information. So when 1 mole of methane is burned at constant pressure, 890 kilojoules of heat is released. Calculate the change in enthalpy through reaction for a process in which a 5.8 gram sample of methane is burned at constant pressure. So this is telling us that even though we don't have a reaction necessarily, we could write a reaction if we needed to, but 1 mole, when 1 mole is burned of methane, 890 kilojoules of energy is released. So that is kind of like our conversion factor. 1 mole is equal to 890 kilojoules. Now, the key word here is released, and so since it's released, that means that it will be exothermic. So we would have negative 890 kilojoules is equal to 1 mole. And we know that we have 5.8 grams of methane burned. So we want to know the change in enthalpy. And remember that we had this before, that the change in enthalpy units will usually be kilojoules per mole, or kilojoules. So we'll just do some canceling of units. 5.8 grams of methane over 1. We can't just go ahead and multiply by 890 kilojoules because it's per mole, not per gram. So we now need to convert to moles of methane by dividing by the molar mass of CH4. And I found that to be 16.04 grams. And then now I'm going to go ahead and just plug in my negative value because I know it's going to be negative at the end because it is an exothermic reaction. The word released tells me that it's exothermic, okay? And that's per mole of methane. So when you multiply that all across, I get negative 322 kilojoules. So for significant figures, negative 320 would be the answer. Okay, so this is just another way that we can use, even though we're not given enthalpy of reactants or enthalpy of products, we can still figure out how much is released for a process given some information. So you could just use canceling of units, dimensional analysis to solve these problems.